and he's the key. He oversees the GPI-2 instrument project with the contribution of other universities as well. And he was kind enough to present us the GPI-2 work we are doing with the collaboration of Notre Dame, Gemini, Cornell, California's San Diego office, and Canada as well. So I will leave it to him, and at the end we will have a time hopefully for questions. Thank you, Jeff.
Sure.
Take it over.
All right. Well, it's a pleasure to talk with everyone today. I want to discuss, or I will be discussing, both GPI-1 and GPI-2 and their ability to reveal exoplanets, what we've learned and what we're upgrading GPI-2 to be, recognizing that GPI might be something that's new to everyone. I want to go through a little bit of GPI's history. The work that I'm presenting is not mine, but is the contribution of a lot of people's, including many, many folks at Gemini's. And so when I end up talking about many folks and discussing how it takes an army or a village to build an instrument, this would be that group. It's broken out into essentially 3 different categories with names that are repeated through all of them. The GPI-1, laser pointers do not work on TV screens very well. The GPI-1 original instrument team, this is the team that built the Gemini Planet Imager, the instrument that went to Gemini South. The Gemini Planet Imager Exoplanet Survey, GPIs, is the large-scale science campaign that GPI undertook. And then GPI 2.0 is the name we gave to the upgrade of GPI, in that it's still the same core instrument. It still has the same core software. It's not a brand new instrument, so it's not 2. It's an update, so it's 2.0. We had a lot of discussions about this. But all these people in the different projects have contributed heavily to the work I'm going to present. And so what I want to go through is a little bit of the history of GPI, its concept, how it was built, the science that's behind direct imaging, and then discussing where that knowledge led us to through the GPI survey, the successes of some of the other science surveys, and then the science goals and the upgrades that GPI-2 is undertaking. And so if we think about the number of exoplanets that have been discovered, the number of planets that have been found, and this is a few years old of the video, has gone from a handful of planets to now thousands of planets. It's over 5,000 now that have been found throughout the sky. And we've seen them all over the sky. It becomes especially exciting when Kepler starts observing, because suddenly there's a bunch of green spots on one specific spot of the sky. But we've now found thousands of planets. And the majority of these numbers have been found via the transit method and the radial velocity method, some via the microlensing method, and then GPI's bread and butter, the imaging method. But you can see that there's a diversity of planets, and each of these tells us different pieces of information. And so, just as a reminder, the radial velocity technique is essentially using the fact that stars are orbiting around the center of mass of their solar system. So if you have a series of planets or a Jupiter-sized planet that is tugging on its central star, the star is orbiting that, we can see the star accelerating towards or away from us, and that causes it to be redshifted or blue shifted. And so we infer that something is causing the center of mass of that solar system to be different and causing that star to wobble towards and away from us. The transit method is essentially where you have a large planet or some other object that's going between you and that parent star. It's blocking out some of the light. If that keeps happening in a repetitive fashion, then you infer that there must be something orbiting around that star. Both of these methods infer the existence of a planet. We don't actually see that planet's light, but we infer that the planet must exist because there's some sort of effect upon its parent star. These methods have been wildly successful and have found thousands of the planets that have given us a wide diversity. But direct imaging is where we actually are looking for the light from the planet itself. And so you can think of direct imaging as, instead of inferring the existence of the planet, trying to see something fairly dim next to something very, very bright. And so the analogy that we often use for this is trying to find a firefly next to a lighthouse. And so if you look at this image, you will see a nice bright lighthouse. If you were to turn off the lighthouse, you would see a little tiny firefly glowing next to it. And now that I've shown you where the firefly is, if I go back, you might be able to see, if you look very, very closely, where that planet was or where that firefly was. That's what we're trying to separate out. We're trying to see this faint object next to this very, very bright object. So the difficulty is the difference in brightness. So if you want to get reflected light that's coming from a planet and you're looking in the optical, you'd want something of a difference of 10 to the 9th brightness. So the difference between the reflected light coming off the Earth or off of a Jupiter and the star's emitted light is about 10 to the 9 in terms of contrast or brightness difference. But if we look into the infrared and we look for planets that are recently formed, we can use a little trick, which is when they're very hot and they've been recently formed, they're glowing, and these Jovians can be about 10 to the 4 times brighter than their parent planet. So if you want to find planets and you want to use a little trick to help you out, you want to look for these young planets. The problem is not the separation of these objects and not even the overall brightness of these objects. But the problem is the fact that you have something really close to something really faint, close to something that's really, really bright. And so if we were to look at two objects that are separated by about the size of a planet, you can see here in blue, one object, and red a separate object. And so something like a 2-meter telescope can see a 1 AU separated Earth at 10 parsecs relatively easily, and on a 10-meter telescope, they'd be extremely easy to see. If these objects were free floating, if you had a free floating planet, the brightness of a recently formed Jupiter, you could easily see that with a 10-meter or an 8-meter telescope. The problem is you have a really bright object next to a really faint object. And so even though we usually only think of the PSF as going through maybe the first airy ring or the second airy ring, that pattern still continues to go down, such that while you have this bright, I don't know why I keep trying to point at this with this laser pointer, while you keep trying to see the relatively bright object here, that PSF function causes there to still be a halo of brightness that takes a very, very long time to decay out, such that even though we have this relatively separated object that on something like Gemini or Keck we could see, it's still far too faint in reflected light. And it's barely at the point where you could see it in thermal light. But it seems that you could take this image and if we had enough knowledge of the PSF, if you took enough sensitivity, took a long enough picture, you could subtract out this relatively bright PSF, and what you'd be left with would be the residual signal from your planet. The problem was, or it's been rapidly recognized, is that telescopes, PSFs at this level are not completely stable. There's things like gravity, thermal effects, the fact the mirror changes, light goes through slightly different paths as you look at different objects. If you're in space, the sun taking slightly different angles and heating up your telescope in slightly different ways means that the PSF, or the speckles, the remaining light, ends up changing on the order of minutes to hours. So I promise you for both of these images that there's planets that are buried behind them. The problem is, even if you have knowledge of the PSF, since it changes over time, it makes it difficult to subtract. Does anyone have any questions? Okay. The brightness of our planets is also a function of their age. And so as the planets get progress in terms of their age, they go from being relatively bright to relatively faint. Those planets can have two different types of populations. They can be either what we call a hot start formation or a cold start formation, and this changes our ability to detect them. If something is formed via the hot start method, which I'm going to explain in a moment, then it can become relatively bright at extremely young ages. If it's formed via the cold start method, it ends up being relatively cool for a significant portion of its life. And so you can think of these two different scenarios as your bottom-up core accretion. This is where you form a central mass of about 10 solid Earth masses of material. That material comes together, and then it forms and pulls in 300 or so Earth masses of gas and dust to form a Jupiter-like planet. This is what we would call the cold start method. This starts off with those series of curves that are lower down. On the other hand, if you have a large, massive disk, then you can have instabilities in that disk. Those instabilities can fragment as the disk is moving around, and those fragments can begin to self-collapse on their own. And in a similar way to thinking about how stars form, those planets can form and be much hotter in their initial formation. But as both of these planets cool down, as they evolve, they end up merging together effectively in their temperatures. So by the time you get to a Jupiter mass planet, at the age of our Jupiter, it's forgotten its formation history. So if we want to understand how many planets we have, what the demographics of those planets are, we need to be able to look at both young ages for these planets and at extremely high contrast for them. If we're able to reach deeper contrast, then not only can we start looking at the diversity of planets, we can look at younger planets, so we can understand the hot start method, we can understand the cold start method, and finding very, very young planets that are close to us is difficult. So by being able to go to a deeper contrast, we can directly image planets that are slightly older. So thinking about all of this, it's bad when you pull out a slide that has the date 2003 on it. Gemini was looking for its next science questions that it wanted to pursue. And so in 2003 underwent what was called the Aspen process at the time. And one of the key questions among many that came out of that was how common are extrasolar planets, including Earth-like planets? This was at a time when not a single directly imaged planet had been observed, and this was very early in the planet process. And so that report or that meeting came about asking for an instrument with new capabilities. That would be an instrument that could operate in the near IR for about 1 to 2.5 microns, that had a spatial resolution of about 0.02 arc seconds, that either had the ability to image in multiple filters simultaneously or was an integral field unit on the order of 30 to 300 in resolution. It had a field of view of about 3 arc seconds. It could look at a total of 1 object at a time. And it would achieve a contrast ratio about 10 to the -7 and would have capabilities in polarimetry. Going back slightly further, there had been a straw man instrument design that had been done for Keck in 2001 to do direct imaging. And so out of those two processes, the Gemini Planet Imager was born. So we're going to jump through 10 years of development and a bunch of work by a group of people, and you get to GPI, which is essentially an advanced high contrast imager with a high order adaptive optics system, a chronograph, an interferometric calibration unit, all feeding a 1 to 2.4 micron integral field spectrograph. This was built by 7 different institutions, both in the US and Canada, and it achieved first light on Gemini South on November 11th, 2013. And about a year later, in 2014 B, began routine science operations. So essentially, it took 2 semesters to commission the instrument and to begin routine science operations. What you can see up here is them assembling the optics onto GPI and then mounting it on the telescope at Gemini South. The GPI team was relatively excited by this when first light was achieved. And so we're all jumping in the air. It was noted that over the 3 nights, as GPI was doing better and better and better, the team was getting progressively happier in their photos until we got to this point by the 3rd night. We also learned that you cannot get an entire group of astronomers to jump all at the same time, no matter how hard you try. But you can take a freeze frame where it looks like everyone has jumped all at the same time. GPI-1 operated at Gemini South from 2014B to 2020A. It had 58 unique principal investigators. And I mentioned there was this GPI's team. So the large-scale survey counts as one PI. That means that there were 57 other unique programs that were awarded time. Many of those had overlaps, of course, with the GPI team. There were 1,700 hours of awarded queue time to GPI. This has resulted in 53 refereed publications. GPI has been cited more than 4,000 times. I'm very happy to say more than 4,000 since it's now 4,001. And that results in about 48 citations per published paper. Now, those 83 refereed publications are just the science refereed publications. That doesn't include the vast history of GPI in committing to SPIE. There's more than 100 different SPIE publications that are contributing to the field. This means that the instrument has an H index of 34, and if you include the instrument papers, it gets to an H index of 37. These papers are not just used by people in science, but they're referenced by other instrument teams. They're referenced by future instruments as the different developments of direct imaging instruments have been able to contribute to each other. GPI resulted just from science data to 14 different PhDs. And it was delivered with a relatively robust IDL data reduction pipeline, which might be Gemini's only IDL data reduction pipeline for an instrument. In that we were advanced at the time, we didn't do IRAF, and yet now we're behind, and we didn't get upgraded to Python. GPI had a couple of key features that were part of its formation. At its core, it has a 4,000 actuator MEMS deformable mirror and a piezo woofer, so it has 2 deformable mirrors in it. It was operated by a spatially filtered Shack-Hartman wavefront sensor with a 6-electron read noise 160 by 160 pixel Lincoln Labs CCD. It operated at 1 kilohertz with about 1.4 milliseconds of delay. It operated down to about 9th magnitude. If the weather was very, very good, it was able to operate down to 10th magnitude. All of its optics were extremely good, less than 1 nanometer RMS wavefront error. And of course, as I mentioned, it operated from 1 to 2.4 microns with a 2.7 by 2.7 arc-second field of view. But that doesn't quite do justice to the number of optics that are in its optical path. There's quite a number. And so you can see the system is broken out into 3 to 4 major components. It's broken out into the adaptive optics system, which you can see here in yellow and blue. That includes the 2 deformable mirrors and a woofer tweeter configuration and the Shack-Hartman wavefront sensor. There is the self-calibration, or known as the CAL, which uses an interferometer and an infrared Shack-Hartman wavefront sensor. And finally, the science light is sensed by a lenslet-based integral field spectrograph. The light has to travel through each and every one of these optics to get all the way to the end. Each one of them does corrections. You have the AO system operating in the optical, the calibrations, or the CAL operating in the infrared, providing pointing and centering updates to the AO system, make corrections in the infrared, and then the final science sensing is done by the lenslet-based integral field spectrograph. GPI found a number of important results, and it's important to remember that when GPI was built, not a single planet had been found yet. By the time it was finished, of course, a couple of them had. But GPI was able to understand each of these planets in a new way. So planets such as Beta Pic B and 51 Eri, Beta Pic B was monitored for GPI by GPI for many, many years, which means that we get this nice little video where you can watch it orbit. We also were able to achieve a spectrum of it and to understand what its atmosphere looks like, and I'll show that in a second. 51 Eri B is the only planet, is the lowest mass directly imaged planet that's been found to date. It was discovered by GPI. And then we have various brown dwarfs and a large number of disks. With the polarimetry mode, GPI was able to look at disks and a large number of objects that you are interested in looking at that might have a planet in them, also might have a disk that you'd be interested in looking at. And I mentioned that GPI was able to do spectroscopy. This means that we can look at each of these planets and to challenge the different models to understand what the planetary atmospheres look like. This is the best fit model at the time that was done for GPI. I can promise you that several of the other models, while they gave the same fit result, looked very, very different. And so understanding what the models of these atmospheres are and feeding back into the theory for planets is important by getting some of these spectra. GPI, the GPI survey, though, was important for understanding the demographics of planets. And so to do this, what GPI was really looking for was to survey about 600 stars. It did slightly less in the end, and this is the results of the first 300, to understand how common planets are. And you have to look at that in terms of both this hot start population and this cold start population and your sensitivity to each of these. And so what you're looking at here is what we would call a tongue plot, but you can think of this as essentially how sensitive was the GPI survey to understanding or discovering these planetary systems, or how common are they? And so you could see something like down here, about 16 stars were observed that could have had planets around them, and we found about 2 objects in there. But this ends up telling us something about planet populations. For cold start planets, on the other hand, I will warn everyone that on the left-hand side, the diagram goes from 100 to 1 Jupiter mass on a log scale. For the next 2 diagrams, it goes from 1 to 10 Jupiter masses. So there's a big chunk that's missing from it above. The GPI survey was not overly sensitive to cold start planets, in that there were only a few stars around which we could have discovered cold start planets. These are for the 2 different cold start models, essentially the Fortney 2008 models and the Sonora models, but both offer a tantalizing glimpse that there might be planets that GPI could observe. But what we learned from the GPI survey was that there are many, many Jupiters here, it appears, or there should be more Jupiters here. And where GPI mostly looked, there's very few Jupiters. So if you wanted to find more planets and to understand the next level of these systems, is you want to either get closer or see fainter, and preferably you'd like to do both. So you'd like to look closer into these systems and you'd want to look for fainter planets. By doing a survey of this size, GPI also had to put together a fairly robust pipeline. This allowed us to analyze the data relatively quickly. When you're looking at 600 stars, you are not going to click through the automated data reduction pipeline 600 times, or the manual data reduction pipeline 600 times. You're going to put the effort into making an automated data reduction pipeline. That served a number of different purposes. It helped the GPI team produce science results faster, of course, because about 4 to 6 hours later, we could have results that were scientifically calibrated. It allows us to re-reduce data, and it also allows us to analyze data to understand GPI's performance in interacting with the atmosphere, GPI itself, and with the telescope. But the GPI data infrastructure is more than just the pipeline that goes along with it. So data, of course, is taken at the summit for GPI. That data is immediately filtered out and sent to both Dropbox and to a MySQL database. That data then goes into the automated data cruncher. This was a system that ran the GPI pipeline, but then offered and ran several more sophisticated processes that are behind it. It then uploaded both information to a web page for anyone on the GPI team to observe, a real-time quick look, so we were actually able to see the results of the data within a couple of minutes of taking data. It uploaded information to a collaborative wiki, and in fact, even uploaded to Slack images that we had seen. So if we had seen something on Slack, it uploaded.
If you remember that we have to interview
The GPI data pipeline is that one of the key points to the GPI data pipeline is that we can reduce all the data in a uniform way. So we can reanalyze pieces of information uniformly as improvements are made. So not only can you analyze the data that's coming off the summit, but when you realize that you've made a data analysis error 200 stars in, you can go immediately reanalyze your first 200 pieces of data. We offered this to not only the GPI's campaign, but there were a number of people who asked us if we would run their data through our automated data structure. So we were able to share that with the community to enhance the scientific output for GPI. That's also allowed us in the years since to reprocess all the data. Now I can't go forward. In a uniform manner. So what you can see is an empirical contrast model for GPI-1 as a function of its star brightness. And so as you go through each bin of brightness, you can see that GPI performs relatively stably, getting slightly worse until you get past 8th magnitude where the AO system had to slow down. This is looking at 25,000 different raw images, 500 combined data sets, and this is extension of work that was done by Vanessa Bailey in her 2016 publication. And what we can see is that by mining the data, GPI's performance is a strong function of tau naught from the Gemini South mass. What we see is that GPI's performance improves substantially as tau naught becomes longer. So as the atmosphere becomes more stable, GPI's performance improves substantially. This helps us when we're thinking about if you want to relocate your instrument, in that Mauna Kea's tau naught is significantly better than Gemini South's. So even relocating GPI-1 from Gemini South to Gemini North would improve the instrument's contrast ratio. Additionally, just tasting some of the different things that GPI has been able to pull out, we can see that effects from the telescope influence GPI's ability to operate. And so this is a comparison of all of the different observations with GPI, looking at the raw contrast. This is the individual contrast out of each image, with a difference between the primary and primary's temperature and the outside temperature's air. And so you can see that as the primary's temperature deviates, you can end up getting dome seeing effects. So if the telescope, if the air conditioning wasn't set to the right temperature for the night, if for some reason the air conditioning was off, if the primary is warmer, the night has a different set of temperatures. It's been many days since any observations were done, and the primary mirror is substantially different in temperature than the outside air, then we can actually see a degradation in GPI's performance and our ability to observe with contrast. And while you can see most of these upward spikes are because of different weather conditions, there's a very nice trend running through here. The system's slightly more stable, we believe, under colder temperatures, because if the mirror is colder, you end up getting a meniscus effect where the air settles on the mirror and then just floods down onto the dome floor. And that doesn't cause as much of an effect as if the mirror is hotter, and it then causes an eddy current to come straight off the mirror and to go up. We couldn't find, the reason this got found and published is, while everyone believes this is true, there aren't any really recent data publications and nothing with AO that we could find. And there is a substantial decrease in GPI's performance. These are just tastes of pieces of information we were able to pull out, but we were able to pull all of these out as we were thinking about how to upgrade GPI-2 and what would it look like if we wanted to migrate GPI-2 from Gemini North to Gemini South. And so as we were thinking about migrating it, we want to start comparing what are the different observing conditions, what is the different tau knots, how would GPI's performance, and would it be worth upgrading? Now, another key important thing is that if you're going to move observatories, you have to change your mascot animal. So this is one of the foxes that was just hanging out near the dorms that like to try and get scraps of food, and is the reason the sign said "Don't feed the foxes." And if you can look on the back of my laptop, it probably isn't seen from here. There's a little tiny fox that was on our logos. Well, we couldn't have a little tiny fox on Mauna Kea, so we had to choose nenes, of course, as an animal if you're relocating from Gemini South to Gemini North. But the key things is to understand how GPI's performance would affect if we went to Gemini North. The other thing is GPI was designed to operate until about 2020 before it needed a major overhaul. Overhaul being an inspection, because there was a given lifetime testing to each one of the mechanisms. Not that anything was necessarily wrong, but when you get to the end of mechanism lifetimes, it would be a good idea to inspect it. So GPI was coming up at a point in time where it would be a good idea to do a major inspection of the instrument. It had gone from 2015 all the way until 2020 without having to be opened a single time. It hadn't had a single mechanical failure. It had had one problem with a mechanism that had occurred in 2015. Otherwise, I would get to say going all the way back to 2014. That took us 1 day to swap out. We had a spare. We were able to reach in and trade it out. It took 2 of us to do it. But otherwise, we were able to operate from 2015 through 2020 without any major mechanical problems. A small issue we'd had was one of the hard drives that had been operating for 10 years of powered on time finally started throwing errors. It didn't fail, but it started saying, I'm ready to be replaced, but that doesn't seem like that's a significant problem. So we were fairly confident in the instrument. We'd been fairly confident in the testing, but it was time to do some maintenance of it. And if we were going to consider, since Gemini South had to take off an instrument and if GPI was the one taken off, if it was relocated to Gemini North, then we should do some sort of an upgrade to the instrument at the same time. If you're going to take it apart, why not put some new technology into it? So this started a process in 2016 to 2017 to discuss with the science community how we could upgrade GPI. And it was to develop a science case to make it relevant for the 2020 to 2030 timescale, while emphasizing several of GPI's key strengths. It had been relatively reliable, 5 years of operation without having a major mechanical problem. It had been relatively efficient in its operations. We wanted to understand, go from the original idea that GPI had been science-driven originally, and that it had gone from science requirements down to practical designs. And finally, Mauna Kea is a very different environment in terms of telescopes than what we have in Chile, in that there's a number of competing observatories who have excellent instruments that are very good for direct imaging. Specifically, Keck and Subaru have fantastic instruments. SkexAO is an amazing instrument that I'm required to say because of all the SkexAO folks who are over here. But the main point of this was not to compete head-to-head with those instruments, to each use each instrument as its strengths allowed. So there had been some proposals that maybe we should add something like a 3 to 5 micron imager to GPI, but NERC2 on Keck is very good about doing 3 to 5 microns. It wasn't clear that GPI would add a significant amount of science case to that when you could just ask if you wanted to do science under the same envelope by going to Keck. GPI is a stable instrument for long-term surveys. And so we went to the community, we asked them to put together a series of discussion points about what would a new instrument upgrade be like to make 2 different leaps. The first was what did they need as a minimum science upgrade or technological upgrade to make the next forward movement in their science progress. The other one was asking them if they sort of had a reasonable wish level, what would they wish for? And using that, we were able to distill that down into essentially 3 different categories: a wavefront sensor eye magnitude improvement, an inner working angle improvement, and a contrast improvement for a number of different science cases. And these became the drivers for how we were going to define the technology to push GPI forward. We have chosen primary science cases and secondary science cases within this. But the first of these is to do a large-scale survey again, just like the GPI survey, and to look for cold start planets. This asked for something around an eye magnitude of 10, an inner working angle of about 0.15, and an improvement of at least 2 magnitudes in contrast. The next push would be something that were very young stars and transition disks. This required fainter operations because we had to look at further away stars. Those further away stars also required us to have a closer inner working angle, but it didn't require GPI to have significant contrast improvement. Asteroids, which was originally part of one of the GPI science goals for GPI 1, would have required us to push the instrument out to 13th or 14th magnitude to look at asteroids within our own solar system. It didn't, of course, have an inner working angle requirement. So since you can observe those objects directly, you don't need to block out the really bright thing because asteroids are not that bright. And it didn't require contrast improvement. Going all the way down through looking at non-direct imaging or non-planetary science campaigns, opening up GPI to look at other capabilities, such as evolved stars and nearby AGN. So to make GPI not just for directly imaging exosolar planets, but if it can do other science cases as well, or we could consider doing other science cases as well, we wanted to be open to that. And so this resulted in a proposal in 2018 to upgrade GPI that was funded. Between the different institutions, we've gotten about $8 million to upgrade GPI. This is a mixture of funding from the NSF MRI. The NSF MRI also has a significant funding component from each of the universities. So Stanford, Cornell, and Notre Dame have had contributed over $1 million total of their own internal money. The Heising-Simons Foundation and the National Research Council of Canada. NRC is upgrading for Cal 2.0, which is being led by Christian Marois and is on a different schedule than GPI itself. And this is being run by myself, Quinn Konopacki, Bruce McIntosh, Dmitry Savansky, and I mentioned Chris Young. But we wanted to see how these different improvements to GPI would affect the sciences. And so what you can see here on the left is every contrast curve that GPI ever achieved. I actually don't think we plotted all of them, but we plotted a random sampling of them. You can see here in gray. And if we assume that GPI achieves a contrast improvement of only 3.2 magnitudes, that's not the exponential magnitudes, that's astronomical magnitudes. And we run a Monte Carlo simulation of the universe using what GPI 1 learned, what other surveys have learned, and then assuming an equal number of cold start planets, we can guess how many planets exist. And what you can see is you're seeing a diversity of blue being cold start planets and red being hot start planets. And if you look at this, you will see 4 red dots that are filled in and 1 blue dot that's filled in. This is running a Monte Carlo simulation of the universe with GPI 1's original survey and the diversity of different contrasts. And what a filled in dot means is that we discovered an object. Those discovered objects, if you notice, there are objects, that are in the contrast regime that GPI would have observed, but of course it didn't observe those. That could have been the planet is too close to its parent star. We observed it in weather conditions that weren't ideal for it. If you're randomly picking out the brightness of the star, you don't always necessarily observe a planet that's actually in your field of view, unfortunately. But we did not program this into the simulation. It found 4 hot start planets and 1 cold start planet, and GPI has found 4 hot start planets and 1 either hot or cold start planet. So we have 5 planets, and the simulation found 5. GPI's science goal, though, is to push the contrast down as a minimum to the black line, which offers a tantalizing idea that you could find a number of planets. And depending upon the size of the survey and the contrast that GPI achieves, you'd be able to find in the northern hemisphere a number of different planets. And so if you imagine that you achieve a contrast improvement of 2, and you look at 200 stars, you should find about 4 new hot start planets. When you're talking about not having many directly imaged planets, 4 is still a big increase. We can do the same thing for cold start planets. We can play the game of what kind of contrast improvement with a survey. So if you're thinking of the same survey that's going to look at 150 to 200 stars, you do 2.5 magnitudes of contrast improvement, you'll find somewhere like 3 to 4 cold start planets. That's a significantly big enough number of planets that we can search through, that we can make estimates on what is the cold start population like, if there is one. If you find nothing, that's informative. If you go from 0 or maybe 1 planet, but we'll call it 0 to 4, that's a big increase in the number of cold start planets. So both of those helped us inform, based upon what idealistic you could do for a survey in size, and what sort of contrast you would want to achieve in order to reasonably make an effect upon the science. The next science case was to look for these very young planets in Taurus. These very young planets, unfortunately, the Taurus star forming region, while being only 1 to 2 million years old, is about 140 parsecs away. The further away your star is, the closer you have to get for your inner working angle. That's hard. GPI was limited to looking to about 100 parsecs, but by being able to push the system to fainter magnitudes and to closer inner working angles, we believe that we would be able to observe some of the youngest planets that have been recently formed. Yes, they're extremely bright, but you're going to have to look extremely close to find these planets. As we mentioned, GPI also wanted to look at non-direct imaging science cases, non-planet science cases. And so there's interest in using GPI for AO-sensitive IR polarimetry, to look for dusty toruses and outflow structures, to look towards these fainter objects such as AGN or planetary or stellar atmospheres that are being blown off, and to look to asteroids. GPI's capabilities allowed it to observe about 1 asteroid originally. If we can push the system down to 14th magnitude, that opens up another 1,300 asteroids that GPI could observe, to understand what does their surface look like with the spectroscopy, to understand possibly some of their structure of their surface, their chemistry of their surface. And if there's binary asteroids, you will now have 2 objects, and you have an ability to observe these 2 objects orbiting around each other. Now, to do all this, it's taken us a while to get to the hardware. To do all this, I've taken GPI and I've broken it down into what were essentially the major components of the system. To make the changes that we want to achieve these science requirements, we are having to upgrade everything that's in green. So that means that we have to put a new AO system in. That means that we have to update our coronagraphs. This is our ability to suppress the starlight, to upgrade our ability to sense tip tilt errors in the infrared, to provide new low resolution prism capabilities in the integral field spectrograph, and then to improve efficiency in operations, to also improve the software that operates in GPI. One of the key things that we learned after operating from a decade is what rough spots occur between us and the observatory. And our goal was to smooth out some of those rough spots to further improve GPI's operability on sky and its efficiency. What gave us hope that we could improve GPI's operations is that the brighter the star got, the further GPI's contrast was able, the deeper GPI's contrast was able to get, all the way down to Sirius, where we achieved a very nice 10 to the minus 7 contrast at about an arc second. So as GPI got more light, or there was more light through the system, we were able to perform better, which means that GPI was not limited by its internal optics. At its core, GPI was able to perform exceedingly well. And so if we can improve its ability to digest light, to look at the images, and to perform on sky with the adaptive optics system, we believe that we could continue to improve its performance. So the first of these improvements is to upgrade the AO system. I mentioned it's a Shack-Hartmann wavefront sensor. To upgrade the AO system to a pyramid wavefront sensor. This was designs that were done by Hertzberg Astronomy and Astrophysics in Canada, simulations that were done at Stanford, and construction that was done at the University of California, San Diego. As I mentioned, it's replacing the Shack-Hartmann wavefront sensor with a pyramid wavefront sensor. It's based upon the nefarious TMT designs. So in fact, we're using some of the design components or some of the spares from TMT's Nefarious. One of the biggest problems was we had to fit within the existing AO footprint for GPI while not affecting any of the deformable mirrors. So essentially just into the Shack-Hartman wavefront sensor's footprint. So it's relatively compact. And to changing the operating speed from 1 kilohertz for GPI 1 to 2 kilohertz for GPI 2. Oh, I forgot I had that. There you go. The parent wavefront sensor uses a double 4-sided pyramid. The mirrors were done by Coastline Optics. Its machined parts were actually made in Canada by OMP. And the moving deformable, or not the deformable mirror, the steering mirrors are by PI. What we're using for GPI, as I mentioned, a 6-electron read noise CCD is what GPI originally had. To allow us to go to fainter stars, we're moving to a 0 read noise, high quantum efficiency EM CCD from Nuvu cameras. It's a CCD 220, which is being used in a number of different AO systems. The difference is our camera is from Nuvu instead of First Light. To provide essentially faster readout for GPI, as I mentioned, to operate at 2 kilohertz. And the idea is to integrate this with the rest of GPI in early 2024. That originally said late 2023, and then the camera had to go back to the manufacturer, unfortunately, for 2 months. And that pushed us over into, right now my schedule says January of next year. Simulations of the AO system, assuming a throughput of 0.32 or 32% throughput, show the system should be able to operate all the way out to 13th magnitude while gracefully degrading out to 14th, and even may operate out to 15th magnitude while achieving a relatively high strel in different seeing environments and being able to operate at 2 kilohertz through almost its entire range without us having to change speeds of the system. Additionally, for the pyramid, we're upgrading the RTC. We're using the HART architecture, which is the same core system as you guys will be using for GNAO. This allows us to share commonality between AO systems to allow each of the different observatory or each of the different pieces of equipment to benefit from knowledge that's learned from the other one, from errors that come from the other one, and to benefit from a decade of technology development that's been done at Hertzberg to deploy Nefarious. Additionally, GPI will use new appetizers. Appetizers are what we use to suppress starlight coming from the system. Do you want me to stop exactly at the hour because I know we started late, or do you want me to?
We will just continue. And
Okay.
whoever can stick around will stick around.
I just wanted to know how fast I needed to go. For your telescope, you have your telescope light that comes in. Of course, light comes to a focal plane. If you put a coronagraph mask, something that blocks out the central starlight, you can block out the central star. The problem with that is that light is a wave, and so it interferes, and you get this nice, annoying ring pattern that we all are very used to looking in astronomy. And so if you block out just the central light, you still have the ringing that's over here. And so you can see in D, even if you blocked out the central light, you still have ringing. GPI 1 used an apodized pupil Leo coronagraph. So not only was it a Leo coronagraph, but essentially what we did was soften the telescope with a Gaussian function. When you soften the telescope, you get rid of those hard ringing edges. And that means that instead of having this very bright thing that's on the left, even if you block out the central coronagraph, you can end up digging yourself nice dark areas by suppressing most of the light. GPI 2, this was state of the art when GPI, of course, was built, but GPI 2 will utilize a new generation of coronagraphs. These are based upon the last 10 years of design work that's been put in for telescopes such as Roman and Luvoir, to redefine how these focal plane masks work. Essentially, these are better at achieving deeper contrast closer in, while sacrificing some of the contrast capabilities outside of the field of view of the instrument. I don't care if there's extra light outside of my field of view, as long as I can achieve a better inner working angle contrast. These are manufactured by Lambda Consulting. We have a variety of different masks since we have to operate under multiple wavelengths for GPI, some of these operate at different wavelengths. Some of these achieve a better contrast at closer inner working angles by even sacrificing some of the field of view of the integral field spectrograph to allow astronomers, depending upon their science, to make different choices that then will finally be, or that they can use. Additionally, inside GPI, as I mentioned, there's an integral field spectrograph. That is the instrument that takes the final science image. Speckles, these interference artifacts, their position on the detector is a function of wavelength. So if you have wavelength information, you can find the object that you care about by looking for the thing that's not moving. But the closer you get to the central star, the less distance something moves for a given wavelength range. In order to achieve a higher wavelength movement, we are borrowing an idea developed by Karas on Skexeo to put in a broadband mode. This will operate at an R of 11.8, but it will operate all the way from Y to J to H to K band. So everything from 1 to 2.5 or 2.4 microns in a single shot. So it's very, very low resolution. It's very broad wavelength range. This is to improve the signal to noise if you're doing a survey, to find planets around fainter stars, and to allow us to get to closer inner working angles. Additionally, we were able to upgrade the higher resolution prism inside of GPI to allow us to, instead of having to split our K-band into two separate bands, to combine our K-band and get a slightly higher resolution in Y and J band. Finally, as I mentioned, in GPI, we want to upgrade the operations capabilities of GPI. This is a screenshot that I randomly pulled. GPI is a complicated instrument. There are lots of green things, lots of red things, and every one of those buttons opens up another window that looks like this, and several of those windows that you open up have buttons that open up a further window. It's a complicated instrument. It's an adaptive optics instrument. It's an IR wavefront sensor on some levels, a very low resolution Shack-Hartman, and it's an integral field spectrograph, all tied into one tiny package, which means that it has a lot of feedback that it gives you, but it can be complicated to operate. One of the goals is to reduce the number of steps required to operate the instrument on Sky, and to upgrade the high-level operations library to improve Q operations and to improve time domain science. If you notice, this is actually a checklist that was generated originally for GPI, indicating this is how we trained new students on the instrument. And honestly, at 3 a.m., it was very helpful to be able to check things off. It isn't as many steps as it looks like. There are several places that say wait or ask the telescope operator to do something. So there's not as many steps as it looks like. And in fact, several of the bottom steps, I think step 25 says monitor the sequence and data for an hour. So watch your data come in is one of the steps. But each one of those, this is still a 24, 25 step checklist, including if it's saying, wait for this to happen, confirm that this has happened correctly. We want to reduce that so GPI is closer to single button operations. Currently, GPI arrived in June of 2022 after about a 24-month shipping delay to Notre Dame. It was offloaded at Gemini South. It drove down, it flew from Santiago to Atlanta. It drove up on a truck. We unloaded it and we put it into the lab. It's since come apart and is in a number of different pieces. Did I put that right? Yeah. We've procured most of the major components. Almost everything is undergoing testing in the individual components. GPI has to come apart in order for us to access the system. It's a lot of complicated things. The AO system is beneath the integral field spectrograph. In order to get to the AO system, you have to pull out the integral field spectrograph, which also means the AO system has to be completed, working, operated, and commissioned and tested before we can put the integral field spectrograph back on. And the goal would be to ship up here to Gemini North in a little less than a year from now, sometime in the summer of 2024. So in conclusion, we're working really hard to upgrade GPI to enable it to study fainter, closer exoplanet populations. By having a new adaptive optics system, they'll be capable of locking on to significantly fainter stars to allow us to observe essentially lower mass planets that are also closer to their parent star, to obtain full spectra, and then with the goal of having GPI delivered to Gemini North sometime in 2024 and on Sky in early 2025. So with that, I should thank our different funding agencies, but I should ask if anyone has any questions. Yes.
I have a question. So one of the nice evolutions since the original survey is now we have a much more radio velocity and especially astrometric data from Hipparcos, Gaia. How does that change your survey plan for GPI2?
So it makes it, so you're essentially asking if we can see accelerators or radial velocity targets. Yeah. So there's two different ways to look at that. If you want to look at those objects, if you want to understand statistically what the universe looks like, if you pre-select objects with that information, you bias your survey. And unless you understand your planetary formation, you wouldn't be able to back out those biases. And so you have to at least do some level of a survey where you aren't biasing yourself, unless you think you completely understand sort of the question you're trying to answer.
You do have some specific goals in terms of separation and mass you're going after for that new survey, right? So you could understand how much of that overlaps, how much a priori information can you pull from these other data sets?
So I think, you're asking, I think you'd understand it in terms of hot start planets. I'm not sure you could understand it in terms of cold start planets.
Okay.
If you're trying to, and even lower mass planets. Lower mass, a little less clear, but for hot or for cold start, we don't have a good statistical number for those a priori. So I think you'd end up biasing your survey sample. It's not, I think there is a very strong case for doing a survey with accelerating objects, but I think you'd want to almost either keep those separate or at least keep those statistically separate when you're doing your statistics.
So your plan is to do to do the survey that's unbiased.
There is a strong case for doing an unbiased survey, especially since GPI is a biased survey. Also doesn't account for things that are or allows you to get away with a less stable platform. So if you want a highly stable platform, that leans itself to wanting to do an unbiased survey. A platform that's at the cutting edge of technology would do very good about finding planets with a biased survey.
Okay.
Great talk, thank you. There was a hardware slide from GPI1, and it was mentioned that 5 of the actuators were faulty. I'm just wondering what impact does that have?
So 5 of the actuators on GPI are faulty. Let me see here if I can find the LEO stops. I think I went past them. So in GPI 1, the way we solved this was actually putting, it's really hard to see, there's little tiny tabs. And so the MEMS effectively is in a pupil plane. So by going to LEO's plane, you can then have a little dark spot that pulls it out. It changes your PSF, but ever so slightly, almost to the point you don't notice it. With the errors that you have, additionally, what was I going to say? GPI 2, we've actually, since we know about this, yes, they are taken out in terms of, you can see the little dots in the LEO stop, it's the bottom left thing, that are meant to block out the light. But additionally, those were included in the appetizer designs. So in fact, the appetizers, if you notice, one of the designs has little dots in it. So the appetizer designs were built with the fact that we knew that there were bad spots in the deformable mirror and to try and suppress those. Would we do a better job if we had no bad actuators? Yes, because then light wouldn't travel through the system as much and wouldn't scatter off components. But if you have 5 bad actuators, or if you have bad actuators, this is a way to suppress them. Also, you won't see as many tabs. Some of them are under the central obscuration where the secondary is. So, yep.
One question for Michael. Online.
Oh, hi. Hi, Jeff. Mike Liu. Great talk. As you know, when GPI and Sphere, and also I think SkexAO as well, collect similar observations for the same set of known planets, oftentimes those observations do not agree. And I think it's an open question to what degree that's an instrumental / data reduction issue, but also scientifically interesting, perhaps some of these sources are variable. I was wondering if you've thought in detail for GPI 2.0 about how this problem might go away, or GPI 2.0 might be helpful in this respect.
So I think there's a couple of things for variability. There was a very nice piece of work that was done by Jason Wang on Keras and SkexAO a couple of years ago for HR 8799, looking for variability of the planets. And the answer that Jason found, essentially looking for more than a full night, was maybe, which is not always the helpful answer that you want out of an observation. It wasn't yes, it wasn't no, it was maybe. The biggest problem we have is, at least GPI, is its photometric accuracy on any given observation. That's a goal for people that they've wanted to solve. We haven't come up with an overall solution for that. It may be easier to cross-calibrate with Keck, SkexAO, and NERC2, because we'll all be on the same mountain. Someone could come up with some justifications for going between the different instruments. But I think that still remains an outstanding problem.